So this time we're going to be talking about Chapter 16 on aromatic compounds. The discovery of benzene was first isolated by Faraday in 1825, who determined that the CH ratio to be 1:1 and named it bicarbonate of hydrogen. Subsequently, in 1834, Mitscherlich, who determined the molecular formula to be C6H6, named it benzene. There are other related compounds with low CH ratios that had a pleasant smell, so they were also classified as aromatic. So in 1866, Kekulé proposed the structure of benzene to be as such, in which you had alternating double and single bonds. This was shortly after the multiple bonds were suggested. While the structure was proposed, it failed to explain the existence of only one isomer of 1,2-dichlorobenzene. Benzene exhibit resonance, so if we look at the resonance in brackets in the double-headed arrow, electrons from the double bond can move to the new state here in the ring, leading to this resonance form. As a result, instead of being a double bond and a single bond being distinct with these distinct lengths, all CC bonds in benzene has a length of 1.397, which is in between the double bond and single bond. Furthermore, it has a bond order of 1.5, which is in between the single and double bond, and you can represent this this resonance actually as the cyclic structure with a circle in the middle indicating that 1.5 bond order. In terms of structure of benzene, so each of these carbons are sp2 hybridized and has an unhybridized p orbital that overlaps around the ring. 6 pi electrons are delocalized over the ring carbons and can be represented here. So benzene can react with bromine, diatomic bromine, in the presence of a catalyst FeBr3. This is chloroform, which is just a solvent, and in this, when it's reacted with this, you have a substitution of the hydrogen with the bromine, and also resulting in HBr as gas. Interestingly, the Br2 doesn't form across the double bond as shown here, rather you just have a substitution. So benzene doesn't have the predictive heat of hydrogenation of 359 negative kilojoules per mole. Rather, it has an observed heat of hydrogenation of negative 208 kilojoules per mole, which is a difference about 151 kilojoules. This difference between the predicted and the observed value is called resonance energy. If we look at the diagram of molar heats of hydrogenation, first starting here, as cyclohexane. The one double bond shows negative 120 kilojoules per mole. When you have two, it's 240. And then, interestingly, when it's conjugated, so when it's one after the other, it's slightly lower than the predicted unconjugated system. And then if we predict the three double bonds, it would be 359, but rather it's stabilized by resonance as shown here with a 208 that we discussed before. Annulenes are hydrocarbons with alternating single and double bonds, so here's cyclobutadiene, benzene, cyclooctatetraene, cyclodecapentaene. So 6-membered is then 6 annuline, cyclobutadiene is 4, so it's 4 annuline, and then subsequently 8 and 10 annuline. So all cycloconjugated hydrocarbons were proposed to be aromatic. However, in the case of cyclobutadiene, it was reactive and it dimerizes before it can be isolated. So it's not necessarily aromatic. Cyclooctatetraene adds Br2 readily to the double bond, so it's not necessarily aromatic. In terms of molecular orbitals for benzenes, the 6 overlapping p orbitals must form 6 molecular orbitals. 3 will be bonding and 3 will be antibonding. Lowest energy molecular orbitals will have all bonding interactions, no nodes. And then as the molecular orbital increases, the number of nodes increase. So if we look at the example, or the diagram shown here, the all bonding, pi 1, is overlapping. Then you have the next level, which is pi 2 and pi 3, in which you have a single node either going vertically or horizontally, and overlapping here and overlapping here. Then the next step after that is the antibonding, pi 4 antibonding, pi 5 antibonding, as denoted by the star. And in this degenerate, or the same level, that's what degenerate means, you have a node, two nodes that cross one another in one direction and in the other direction. And then finally you have the antibonding, all antibonding molecular orbital, which is denoted as pi 6 antibody or pi 6 star, in which you have three nodes and all of them are opposite. If we look at the first molecular orbital of benzene, it's entirely bonding with no nodes. So all of the bonding orbitals are overlapping, and it has very low energy because it has 6 bonding interactions, and the electrons are delocalized over all the 6 atoms. The intermediate molecular orbital, so this is pi 2 and pi 3, in which you have an antibonding going vertically and horizontally. These two are degenerate, meaning they're equal in energy, and they both have this nodal plane. All antibonding molecular orbitals, so we're going to skip pi 4 star and pi 5 star and jump all the way to pi 6 star, has 3 nodal planes. Each pair of adjacent p orbitals are out of phase and interact destructively. So in terms of the energy diagram for benzene, 6 pi electrons fill the 3 bonding orbitals, so the energy levels are 1, 2, 3, 4 star, 5 star, and 6. And you're going to fill those 6 electrons, and so all bonding orbitals are filled, right? And resulting in a stable arrangement in the terms of benzene. If we look at cyclobutadiene, the pi 1, all of them are bonding, right? So they're overlapping. Then you have anti-bonding, right? We have a node going vertically as well as horizontally, which would be pi 2 and pi 3. Then finally you have pi 4 star, in which you have, right, 2 nodes, and then all of them are antibonding. If we look at the electronic energy diagram for cyclobutadiene, right, the lowest energy is pi 1, and then you have the pi 2 and pi 3, and then pi 4 star, which is the all antibonding. Then you're going to fill those 4 electrons, right, 2 go here, and then 1 each here because it's following the Hund's rule. This is a diradical. As a result of this diradical, this is very reactive, and as a result you have dimers of cyclobutadiene forming. The energy diagram for an aniline has the same shape as a cyclic compound with one vertex at the bottom, and so this would be the polygon rule, in which you put the bottom to be one vertex, and then you line up, draw out the shape of the actual aniline, and then you fill your orbitals according to how many electrons you have in the system. Polygon rule gives you a very fast way to draw electronic configuration. Also, it provides a quick check on molecular orbitals you might draw to see which ones are bonding, antibonding, and non-bonding. So there are certain requirements for a structure to be aromatic. Structure must be cyclic with conjugated pi bonds. Each atom in the ring must have an unhybridized p orbital, so sp2 or sp. The p orbital must overlap continuously around the ring, and the structure must be planar or close to planar for effective overlap to occur. Delocalization of the pi electrons over the ring must lower the energy or electronic energy. So if we look at non-aromatic compounds, such as this, here you have only 2 double bonds. Even though it's conjugated, this is similar to a non-cyclic, right, molecule shown here. Non-aromatic compounds do not have a continuous ring of overlapping p orbitals and may be non-planar. Anti-aromatic. So cyclobutadiene is actually anti-aromatic. It's less stable than just having a 4 conjugated system, right? So this is more stable than this. Anti-aromatic compounds are cyclic and conjugated with overlapping p orbitals around the ring, but electron delocalization increases at its electronic energy. So once you have met the aromatic criteria, you can apply what is called Huckel's rule. If the number of pi electrons is 4n plus 2, the system is aromatic, where n is an integer. If the number of pi electrons is 4n, then the system is known to be anti-aromatic. So the thing to note is that Huckel's rule is commonly used to determine aromaticity and anti-aromaticity. A continuous planar ring of overlapping p orbitals is required for the rule to apply. Otherwise, the system is then non-aromatic. So if we look at the overall orbital overlap of cyclooctatetraene, cyclooctatetraene assumes a non-planar tub conformation and avoids most of the overlap between the adjacent pi bonds. And in this case, Huckel's rule doesn't apply, right? So then if we, taking all the rules into account, if we take 4-annuline, which was the cyclobutadiene, that is by definition anti-aromatic, right? Because it's going to be 4n. 8 annulines would be anti-aromatic, but it's not planar. And because it's not planar, it becomes non-aromatic. 10-annuline is aromatic except for the isomers that are non-planar, and larger 4n annulines are not anti-aromatic because they are flexible enough to become non-planar, so they become non-aromatic. We look at 10-annuline. So you can have the all-cis form of the 10-annuline. This will lead to a non-aromatic system because it's not going to be planar. 2-trans, this is also non-aromatic, but naphthalene is aromatic. So either the cis and the trans will be non-aromatic because planar conformation is not retained, but naphthalene is planar, and as a result is aromatic. So if we look at MO, or molecular orbital derivation of Huckel's rule, aromatic compounds have this 4n plus 2 electrons and the orbitals are filled. So if we look at the, aromatic, 2 electrons are usually at the bottom, right? So that's the lowest energy. And then you have your n-filled shells, in which you have either all of these shells, at least 4 electrons, being always full. So they're full and they're paired. In the case of anti-aromatic compounds, which only have 4n electrons, they have unpaired electrons into generate orbitals. So shown here at the very lowest occupied molecular orbital, you're going to have unpaired electrons. As a result, it's going to be highly reactive. So in terms of cyclopentadiene and the ions, you can have the cation or the anion. In the case of the cation has an empty p orbital and 4 pi electrons, so it becomes anti-aromatic, right, because it's unpaired, right? In the case of the 6 electrons, that's the anion. Cyclopentadienyl anion will be aromatic because it has paired electrons in its molecular orbital. We can deprotonate cyclopentadiene. So cyclopentadiene has a pK of 16. In the presence of a base, we can deprotonate here. So let's do this. Electrons will pluck this off, and then electrons will go into that carbon. leading to the cyclopentadienyl anion shown here. That will generate 6 pi electrons, and you can then actually designate this, as you had shown before with benzene, as the pentane with a circle in it with a negative charge. So by deprotonating the sp3 carbon of cyclopentadiene, there will be a pair of electrons in one of the sp3 orbitals, and these sp3 orbital can rehybridize to a p orbital. So the 6 electrons in the p orbitals can be delocalized over the 5 carbon atoms, and the compound becomes aromatic. If we look at the orbital view of deprotonation of cyclopentadiene, here is cyclopentadiene. This is sp3. Electrons will come and pluck off this hydrogen and go in here, and it'll form a p orbital, right? So the deprotonation allows overlap of all the p orbitals of the molecule, and cyclopentadiene is not necessarily as stable as benzene, but it reacts, and as a result will react readily with electrophiles, right? Because it's nucleophilic because of the 2 electrons. So that ends this part 1 of this chapter.